In this video, I will talk about the backpropagation from output to the hidden layer. So it means that we will talk about the machine learning solution, y hat, and then I move back by applying the derivatives and then reach at the input layer. That is the aim of or this video. So first of all, we already discussed J, which was the error. Previously, we called that as E. It was E in our previous video, since we were only discussing the two input and one output value. So that's what we did in our previous video. Now we want to change this for another variable. The another variable is j. We call the error by j, and then we add a summation. It means that you have not only one value but more than one output. This is the output. This is the output. I will explain this image to you since it is required for the current lecture. We have 1 by 2 y minus y hat whole square. I repeat here, we want to find the error, and to find the error we choose the square of the error term, and then we have 1 by 2, since when we differentiate j, which is error in this term, which is called squared error, when we differentiate j with respect to y hat, then this 2 will be cancelled out from this 2 so that we do not get an extra 2. So this was the j, this is the j in current lecture. Now come back to the image. This is the input. Then we have weights. This weight, and then we have 1, 2. For the neuron, there are neuron over here. 1, 3. Then we have 2, 1. Then we have 2, 2. Then we have 2, 3, so on. All the weights are here. In our previous video, we saw that writing these weights like this is not a feasible thing to do. What we do, we call that all the weights a matrix W1. It is a W1. And this is the, here the one shows we have input layer 1. The 2 shows that we are at the hidden layer. These 2 are hidden layers. Hidden layer mean 2. So different people call it differently. If this was 0 input, then this was 1, you can call it the output as 2. But here, this is 1, this is 2, and this is 3. That's why we have 3 over here in the output superscript. This is Z11 is the linear combination of all weights which multiply, which are coming from the inputs towards it, its first neuron. Okay, I will not explain that since we discussed this in our previous video. So when we have a linear combination of weights with x1 and x2, then we need to apply the activation function on this z value, which is z of 2. Then we get all the values over here, the first value, the second value, and the third value, since we have 3 neurons over here. So it means that when we multiply x w1, we get z, which contains all these values over here. That may be called z2. Then we have, when we apply activation function on z2, you get these 3 answers at the end. These are the output. These output becomes an input. So what we do, we again consider weights, and Z3, which shows that we are at third, which is output, third layer. Z3 will be a linear combination of these 3 values with these values. We again apply the activation function. So W2 shows that all the weights will be accumulated in the W2, in W2. Okay. So J will be equal to y minus y hat whole square. This is just an error. Again, we want to change this in terms of f, activation function. We can write, for example, y hat, the value of y hat can be obtained when we apply activation function on Z3. Z3 can be obtained when we have these 2 values multiply together, and these values can be obtained when we apply activation function on this value f of z2, and z2 can be obtained when we multiply this with xw1. So this is all the process that we need to follow, and I want to write this whole process over here. Okay, so what we get in different color, we get f, which is activation function. This activation function will act on some solution. The solution will be xw1. The solution of xw1, x contains this input and w1 contains all the weights. So we have xw1 over here. The result of that value will multiply with w2. What is the result? The result is this value, which you may call it a vector or something like that. So we have finally xw1, that is coming from the multiplication of this x, which is x, and these are all the weights, and w1. And we multiply, after getting the result, we multiply that with w2. Okay, and then just a square. Then you can get y hat. Okay, I hope you got the point. If you do not get the point, then go back to the video and repeat this conversation. Maybe I can repeat here again. xw1 give you z1, then you apply activation function on z2, you get this value. Then you multiply that value with the W2. You may call that with A, and we will call it in the future this value as A. And A will contain A211, A212, A213, linear algebra. Okay, now the procedure is the same. We need to differentiate that. I will not go into that detail as much. So I just, for example, process it very quickly. Let me just make some space, this thing, and then this image over here. Then we have some place over here. That's it. Okay. Now I need to differentiate partial by partial W summation 1 by 2 y minus y hat whole square. That will be equal to y minus, you need to take a derivative of this whole term over here, and y is just an exact value. Our concern is with w, and w is over here. y minus f x w1 w2 square whole square, and apply the chain rule, partial by partial w, y minus y hat. This is the derivative of j with respect to w. Now we differentiate this again with respect to w2 and w1. Okay, j with respect to w2, and that will be equal to partial by partial w2 summation 1 by 2 y minus y hat whole square. Then we have y minus y hat partial by partial w2 y minus y hat, so on. Then we have, after simplification, y minus y hat partial by partial w2, and we get only y hat. And you know that we have, since y is just a constant value, so the derivative of y hat will survive over here, and then we have minus over here. Okay, we know that from this image the y hat will be equal to f of z3. Then we can write partial j by partial w2, that will be equal to minus y hat partial y hat by partial w2, and we have minus y hat partial y hat divided by partial z3 and partial z3 by partial w2. So we need to apply the chain rule. We also know that, as I already discussed, z3 can be obtained when you multiply this whole a with w2. So it will be a w2. A w2 gives you z3. 3 means the output value. So we have z3 is equal to a2 since A appears in hidden layer 2, W2 weights of hidden layer 2, so we get partial Z3 by partial W2, that will be equal to A2. Now, since we have activation function over here, F activation function, we talk about the sigmoid function, F of Z3, that is y hat, that will be equal to 1 plus e raised to power minus Z3. So it means that we have partial y hat by partial Z3, that will be equal to f dash Z3, that will be equal to e raised to power minus Z3 divided by 1 plus e minus Z3 whole square. One comment is due over here. You can see yourself that we need to take a derivative of the activation function. That's why we use we use carefully the activation functions whose derivative is very easy to obtain, and we can take a derivative of this activation function very easily. This is the activation function. I already discussed the activation function before. So we have partial j by partial w2, that will be equal to, now we are talking about the j with respect to w2, we are back to our derivatives, minus y hat f dash z3 a2, that was over here a2, so on. You can simply replace the values over here that we obtain from the derivatives. Okay, let me just call the variable w3. W3 will be equal to minus y hat f dash z3, as we did our previous video. We are calling this as w. So partial j by partial w2 will be equal to w3, and we have a2. Okay, now you can see that a2 is a column vector, and w delta 3, not w, delta 3 is some column vector as well. Okay, so we need to introduce the transpose over here. So we should write it as partial j by partial w2, that will be equal to a2 transpose and w3. That is the partial j by partial w2. So we have completed the derivative of j with respect to w2. So where we are now in the image, we are in this scenario from output to the hidden layer. Now the next thing is we need to take a derivative of j with respect to w1, since we want to optimize the weights of w1 as well. And I will continue this procedure again. This is a bit easy since we already understood this concept from output to the hidden layer. Now from hidden layer to input, we reach at out hidden layer to input, hidden layer to input. Okay. Now the procedure is backpropagation from hidden layer to input. It means J to hidden layer, then hidden layer to input. So take a derivative of J with respect to W1, that will be equal to partial by partial W1 summation 1 by 2 y minus y hat square. Just take a derivative and apply the chain rule, partial by partial W1 summation y minus y hat. Then we have minus y hat partial by partial w1 and summation y hat, since y is just a constant, and y does not contain, in other words, y does not contain w1. Again, y hat is, we know that this is the value of z3 when it is applied on the activation function, or you may say when activation function is applied on z3. So we get partial j by partial w1 minus y hat by partial w1, that is minus y hat partial y hat partial z3, since w1 can be reached when first you need to take a derivative with respect to z3, so it means we apply the chain rule, partial w1. Y hat is a function of z3 and z3 is a function of w1. We know that partial z3 is, with respect to w1 is equal to partial z3, and we also have to apply the chain rule again, partial a2, and partial a2 actually contains partial w1. This is very interesting. This is a good mathematics. So we have z3 over here. Let me see. Okay, partial j by partial w1, that will equal to y minus y hat f dash z3 partial z3 by partial a2 by partial w1, and z3, again z3 is equal to a2 w2. So the derivative of z3 with respect to a2 will be equal to w2 transpose. We define again w3 W3, I'm sorry, not W3, the delta 3 will be equal to minus y hat f dash z3. So partial A2 by partial W1 will be equal to partial A2 by partial Z2, partial Z2 by partial W1, and partial J by partial W1. So we have, after putting these values over here, we have W3, W2 transpose, since these are the column vectors and row vectors and so on, we need to be careful with the transpose, the multiplication and some other properties which are required for row vectors multiplication, so on. Partial Z2 by partial W1, and A2 will be equal to, when we apply activation function of hidden layer answer Z2. So we have partial A2 by partial Z2 equal to f dash Z2, and we know that Z2 will be equal to xw1, as you can see from the image. Z2, Z2 means we are talking about this term, this column vector Z2, that can be obtained when we multiply xw1. So we get this value. So we have partial Z2 divided by partial W1, which will be equal to x. Partial J by partial W1 are actual derivative. The J with respect to W1 becomes X transpose. W3 are defined variable. W2 transpose, and we have F dash Z2, etc. Now again, if we define delta 2, for example, it is W3, W2 transpose, F dash Z2. So finally we get partial J by partial W1, that will be equal to X transpose delta 2 over here. Okay, so we obtain all the derivatives, the derivative of J with respect to W1 and the derivative of J with respect to W2. The only thing is left over here is to update the weights. The first new value will be equal to the old value minus alpha, which is the learning rate, partial J by partial W1. W1 is a column vector. Similarly, we can update W2 new, that will be equal to W2 minus alpha, partial J by partial W2. That is the interesting thing over here, since we dealt with the column vectors and the row vectors. So this was all about the calculations of derivative, the derivative of error terms, so on and so forth. You just need to follow this course. Otherwise, if you take a look on other courses available, probably you will never understand the machine learning. This is the basic, where we have, for example, the activation functions we defined earlier. Then we have backpropagation, column vectors, matrices, so on and so forth. That's what is the essence of machine learning. Thank you for watching.